You've done a lot of work so far with predicates. You've learned what they are and how they are related to propositions, how to quantify them, how to negate them, and more. Great job so far. But there's one question left to think about. What happens when your predicate has more than just one variable? Let's let P of xy be the statement x times y is bigger than or equal to 0. To determine the truth value of this, we need the values of not just one, but two inputs. For example, P of 2, 3 is true, and P of 2, negative 4 is false. We saw in the last two videos that quantifying the variable turns a predicate into a proposition with a definite truth value. Does that work for two variable predicates? Let's suppose we took P of xy and quantified the variable x by saying for all x, P of xy is true. Unlike earlier, this is still an underdetermined statement because we've quantified the x variable, but the y variable is still unknown. Quantifying the x variable turns a two-variable predicate with variables x, y into a one-variable predicate with variable y. It's still a predicate, and unless we do something with the y variable too, we still can't determine its truth value. The general principle here is that for two-variable predicates, both variables must be quantified before we can say anything definite about truth values. Let's keep the universal quantifier here on x. There are two ways to quantify the missing variable y, universal or existential. If we universally quantify y, we would have this in notation. For all x and for all y, P of xy is true. In plain language, this would say that x times y is positive for every possible pair of inputs x and y. Now this statement has a definite truth value, namely false, because I can find a counterexample easily. For example, x equals 2 and y equals minus 4. So it's not the case that P of xy is true for all values of x and y. But we could have also existentially quantified y to get this. For all x, there exists a y such that Pxy is true. Or, in plain language, for every real number x, there is some other real number y such that x times y is positive. That statement also has a definite truth value, namely true. Let's see why. Where you're sitting right now, pick any real number you like. Now, no matter what number you picked, one of three things must be true about it. It's either negative, positive, or 0. I will now tell you the y value that will make xy bigger than or equal to 0. If your x was positive, let y equal plus 1. If your x was 0, also let y equals plus 1. In that case, x times 1 is either positive or 0, which means P of x comma 1 is true, no matter what your choice for x was. Now, if your x was negative, choose y equals negative 1. Since x was negative, x times negative 1 is positive, so P of x minus 1 is true. Therefore, for every x you might choose, no matter its value, I can find a y value. There exists a y value that makes P of xy true. What would happen if we had existentially quantified the x earlier instead of universally quantifying it? Well, we'd still need to quantify the y variable to end up with a fully determined proposition, and there are two ways to do that. You could have there exists an x such that for every y, P of xy is true, and you could have there exists an x and there exists a y such that P of xy is true. Now pause the video and see if you can determine which, if either, of these two statements is true. There exists an x such that for every y, P of xy is true is in fact a true statement. The statement is claiming that at least one x exists such that x times y is bigger than or equal to 0 no matter what y you choose. And that's true. Can you guess what x value it is? It's x equals 0. If you choose x equals 0, then x times y is 0, which is bigger than or equal to 0 for every single y value. There exists an x and there exists a y such that P of xy is true is also a true statement, because I can certainly find an example of x and a y where x times y is bigger than or equal to 0. For example, x equals 1 and y equals 2. So given a two-variable predicate, p of xy, there are at least four possible ways to quantify it, one for each combination of quantification of x and y. Each way has its own truth value that it's our job as mathematicians to explain why the truth value is true or why it's false. Now, I say there are at least four truth values because, in fact, sometimes the ordering of the variables matters too. For example, look at the predicate q of xy, which is the statement x times y is less than 1, where the x values are integers and the y values are non-zero real numbers. Look at the statements for all x there exists a y such that q of xy, and there exists a y such that for all x q of xy. You might think these statements are equivalent since all we did was change the ordering of the quantifiers, but look at each one. The statement for all x there exists a y such that xy is less than 1 is true, and here's an explanation. Choose any integer you like. If you chose an x that was 0 or negative, set y equal to 1, and then therefore x times y is less than 1. If you chose an x that was positive, set y equal to 1 over x plus 1. Then x times y is x over x plus 1, and because the denominator is bigger than the numerator, the fraction is less than 1. That explanation, notice, does not depend on any specific examples. It works for all x. However, the statement that there exists a y such that for all x, xy is less than 1 is a false statement. I will explain why no such y exists. Suppose that we did have a y such that xy is less than 1, no matter what the x is. Now this y can't be 0 because 0 is not in the domain. Given that fact, it's not the case that xy is less than 1 for all values of x, because I can find a counterexample, x equals 1 over y. If x is equal to 1 over y, then x times y is 1 exactly, and that's not less than 1. So in other words, the order in which we place the quantifiers can sometimes matter. It takes careful mathematical reasoning to see when these statements are true and when they are false. But that's what this whole course is about, so this is good work to engage in. That brings us to the end of this module on logic. You are learning a lot, so congratulations. Our next module is about two more fundamental mathematical concepts that underlie computer science: the concept of the set, which is the model for all data structures in computer science, and the concept of the function, which is the model for all programs. Pretty big ideas, in other words. See you there.